The Antonio Project presents Inner Gas System Part 3 Inner Gas Definition in Maritime Industry.
Hello everyone, welcome back to my channel. I do hope that all of you under great condition. In this part, I would like to discuss about another definition of inner gas used in maritime industry. In the fast and unpredictable world of maritime transport, safety is not just a priority, it is necessity. For tanker vessel carrying volatile cargo, one system stands as a silent guardian, ensuring safety against one of the most dangerous threats at sea, that is, fire and explosion. Let's meet the inner gas system, a critical innovation designed to protect life, cargo, and the environment by replacing flammable gases in cargo tanks with inner gas. This system creates a safe atmosphere, preventing the risk of combustion from oil tanker, chemical carrier to gas carrier. The inner gas system is a cornerstone of modern maritime safety, blending advanced technology with meticulous engineering. As previously being discussed, that inner gas is a gas that does not readily undergo chemical reaction with other chemical substance. Then, how inner gas involved in maritime industry to prevent fires and explosion? So, grab your favorite drinks, get comfortable, and let's get started. Let's go!
Inner gas in maritime industry. Inner gases are widely used in the maritime industry, primarily for safety and operational purposes, especially in hazardous cargo tank management and fuel systems. As previously discussed, the term of inner gas is context dependent. In maritime industry, as per International Safety Guide for Oil Tankers and Terminal or ISGOTT, the term of inner gas defined as a gas or a mixture of gases such as flue gas containing insufficient oxygen to support the combustion of hydrocarbons. Oil Companies International Marine Forum or OCEIMF recommends that all oil tankers, regardless of size, be equipped with inner gas generators to enhance safety. New statutory requirements for fixed inner gas systems entered into force on 1 January 2016 as a result of changes to SOLAS, the Fire Safety System or FSS code, and the International Bulk Chemical or IBC code. International Maritime Organization or IMO regulations have progressively mandated the installation of inner gas systems on tankers of various sizes, with the latest rules covering all tankers of 8,000 deadweight per liter. Composition gases in flammability diagram. A flammability diagram is a graphical representation used to illustrate the flammability limits of a gas mixture in air, typically showing the concentration of fuel, oxygen, and inner gases. The composition of gases in a flammability diagram is divided into three main components. Air mixture, a mixture of gases that compose the Earth's atmosphere. Air composition mainly consists of nitrogen 78.09%, oxygen 20.95%. Other gases below 1%, and 5 of these gases are noble gases. Inner gas definition based on ISGOTT code. A gas or a mixture of gases such as flue gas containing insufficient oxygen to support the combustion of hydrocarbons. The gases are as follows: noble gases, nitrogen, carbon dioxide, and so on. Hydrocarbon or HC. A hydrocarbon is an organic compound that consists exclusively of hydrogen and carbon atoms. Hydrocarbons are the primary constituent of fossil fuels, such as oil and natural gas. Flammability triangular diagram or ternary plot. We will learn to draw a flammability triangular diagram or also known as ternary plot. It used to represent all the possible mixtures of a three-component system. The diagram shows the control of flammability in mixtures of fuel, oxygen, and inner gas, typically nitrogen. The diagram implicitly using the features that the sum of all three components is 100%. This diagram is for methane or CH4 as fuel and located at left leg, nitrogen on the right leg, oxygen on the bottom. Air line, the percentage of oxygen in the air is 20.95%. Lower flammability limit or LFL, the lowest concentration at which a mixture of flammable vapor or gas and air is flammable. Lower flammability limit of methane is 5%. Upper flammability limit or UFL, the highest concentration at which a mixture of flammable vapor or gas and air is flammable. Upper flammability limit of methane is 15%. Limiting oxygen concentration or LOC, the minimum concentration of oxygen required to produce a flammable event when mixed with a flammable vapor or gas in any concentration. Limiting oxygen concentration of methane and to air is 12%. The stoichiometric line, the line that shows the concentration of substance in a mixture that is in the correct ratio to react with another substance. The stoichiometric concentration of methane in oxygen is 1 mole of methane to 2 moles of oxygen. CH4 plus 2O2 create CO2 plus 2H2O. The result of calculation the stoichiometric concentration of methane in oxygen is 33.33%. The lower limit of methane in oxygen can burn is 5.1% and the upper limit is 61%. The brown shaded area shown in this animation is flammable mixture area. This is illustrated in animated diagram where only mixtures within a loop-shaped area are capable of burning. In order to prevent or extinguish fires, inner gas is used by increase the inner gas concentration. Inner gases suppress fires primarily by reducing the oxygen concentration in the environment to a level where combustion cannot be sustained. When inner gas, in this case is nitrogen, concentration being increased, the concentration of methane and oxygen will reduce. Then the flammability mixture are decreased from upper flammability until reach low flammability level. And when inner gas is continuously added, then no fire can form in gas mixture below low flammability limit, even when oxygen is added. Adding an inner gas to a hydrocarbon gas-air mixture increases the lower flammability limit concentration and decreases the upper flammability limit concentration. And that is the principle of how inner gas work to prevent or extinguish the fire. Flammability composition diagram or flammability diagram. Next, we will learn about flammability composition diagram, also known as flammability diagram or combustion diagram. It's a graphical representation used to illustrate the condition under which a mixture of fuel, oxygen, and an inner gas like nitrogen can ignite or sustain combustion. The percentage of oxygen in the air is about 20.95%. Other gases except methane and hydrogens considered as inner gas. In total, the concentration of inner gas is about 79.05%. Oxygen and hydrocarbon mixture in the air calculation is as follows. The formula is oxygen times air minus hydrocarbon divided by 100. For example, when hydrocarbon concentration is 5%, then the concentration of air and hydrocarbon mixture is 19.90%. When hydrocarbon is 30%, then mixture is 14.67%. When hydrocarbon is 70%, then the mixture is 6.29%, and so on. When hydrocarbon and air mixture values are being connected, it creates a slope line of mixture between hydrocarbon and air. In the flammability diagram, slope or slant line of hydrocarbon and air mixture indicates with point A, B. Following is excerpted from ISGOTT code 1.2.2 Flammable limits. The flammable limits vary somewhat for different pure hydrocarbon gases and for the gas mixture derived from different petroleum liquids. Very roughly, the gas mixtures from crude oils, motor or aviation gasoline and natural gasoline type products can be represented respectively by the pure hydrocarbon gases propane, butane, and pentane. Table 1.1 gives the flammable limits for these three gases. It also shows the amount of dilution with air needed to bring a mixture of 50% by volume of each of these gases in air down to its low flammable limit or LFL. This type of information is very relevant to the ease with which vapors disperse to a non-flammable concentration in the atmosphere. In practice, the lower and upper flammable limits of oil cargoes carried in tankers can, for general purposes, be taken as 1% and 10% by volume, respectively. Line AB, hydrocarbon gas or air mixtures without inner gas. Point C, low flammability limit or LFL of hydrocarbon. Point D, upper flammability limit or UFL of hydrocarbon. Point E, as inner gas is added to the hydrocarbon gas or air mixture, the flammable range decreases until point E. It is reached where the LFL and UFL coincide. This point corresponds to an oxygen content of approximately 11%. Area CED, flammable area. Only in this area the mixture are capable of burning. Line FA, dilution with air, changes of composition due to the addition of air. When air is introduced into an inner mixture such as that represented by point F, its composition moves along the line FA and therefore enters the shaded area of flammable mixture. Line GA, critical dilution with air. The line GA passes by just touching the flammable range portion of diagram. Line FI, dilution with inner gas. The line FI when air is introduced into an inert mixture. Line HA, dilution with air, safe area which is not past flammable area. Points to the left of the line AB represent mixtures with their oxygen content further reduced by the addition of inner gas. As the inner gas content increases, the flammable limit mixture changes as indicated by the lines CE and DE, which finally converges at the point E. ISGOTT Code Chapter 7.1.1. As inner gas is added to hydrocarbon gas or air mixtures, the flammable range progressively decreases until the oxygen content reaches a level generally taken to be about 11% by volume, when no mixture can burn. Hydrocarbon gas normally encountered in petroleum tankers cannot burn in an atmosphere containing less than approximately 11% oxygen by volume. The International Convention for the Safety of Life at Sea, or SOLAS 1974, as amended, requires that inner gas systems be capable of delivering inner gas with an oxygen content in the inner gas mean of not more than 5% by volume at any required rate of flow, and of maintaining a positive pressure in the cargo tanks at all times with an atmosphere having an oxygen content of not more than 8% by volume, except when it is necessary for the tank to be gas-free. For example, measure value of mixed hydrocarbon and oxygen in the cargo tank are as follows. Hydrocarbon is 11% and oxygen is 5%. This is shown at point F. In this condition, air introduced to the tank or aeration. Then, while diluting the mixture of hydrocarbon and oxygen, it will pass through the flammable range. Choose critical dilution limit with air, or GA, is the minimum amount of purging required to ensure that the mixture doesn't fall in flammable range while diluting with air. To be on the safer side, to continue purging the mixture from point F even beyond the critical dilution limit with air to prevent any fire hazard due to purged mixture passing through flammable range during dilution with air. The purging is continued till the mixture reaches point H. From point H, if the mixture is diluted with air of 21% oxygen, it will follow the line HA, which doesn't fall in flammable range. Hence, safe condition is maintained throughout the process. It is well understood that the use of inner gas itself doesn't guarantee the safe environment of tank during tank operation until inner gas vision is above the critical limit of the environment.
This is the end of inner gas system, part 3, about the definition of inner gas in maritime industry. In conclusion, the differential definition of inner gas between classical definition and in maritime industry, while in classical definition, inner gas unable to react with other elements to form compounds. Meanwhile, inner gas in maritime is a gas or mixture of gases which containing insufficient oxygen to support the combustion of hydrocarbons. Anyway, we will dive deeper about inner gas used for tanker vessel in next inner gas system part 4. That's all for now. Let me know your thoughts in the comment below. Bye-bye.
Thank you for your time to watch my video. Be sure to hit like button, subscribe if you haven't already, and ring the notification bell so you never miss an update. That is the best way to support what I do to share knowledge.
Thank you for watching my video. Terima kasih. Di Antonio Project.